Good morning. Today we will continue with the topic which we were discussing in the last class. We'll continue with low hydrogen electrodes. This slide was presented during the last class, basically regarding what is AWS nomenclatures of electrode. So before proceeding further into our lecture today, I will give a brief revision of the nomenclatures of electrodes. You can see in the picture that one electrode E7018 is displayed. I had mentioned that wherever E is mentioned, it shall be read as electrode. Wherever R shall be mentioned, it shall be read as rod or filler rod. So E denotes electrode. The figure shown here basically shows four characters after the alphabet E. 7018. It can be also five characters like 10018, etc. The first two digits of a four character electrode or three digits of a five character electrodes indicate the minimum tensile strength of the well produced in KSI. The electrode shown here depicts 7018, which shows 70 KSI will be the minimum tensile strength of the electrode of the well produced. The next to last digit, in this case 1, denotes the position of the position of welding that is possible with the electrode. 1 denotes all position welding, and the last character 8 denotes the type of coating. It can be either 0, 1, 2, 3, 4, 5, 6, 7 or 8. And this was displayed in the last presentation as well. It not only denotes the type of coating but also the welding current characteristics. Say for example, it can be positive terminal of the DC or negative terminal of the DC, or can be an AC current flowing through. The electrode which is shown here has a last digit 8, which depicts low hydrogen potassium binder with iron powder. Low hydrogen electrodes are broadly or generally known as basic electrodes as well. These basic electrodes, the nomenclature came because of the presence of more than 50% of limestone or calcium carbonate. This limestone or calcium carbonate, when exposed to arc, will decompose and form carbon dioxide and carbon monoxide, which predominantly acts as the shielding gas protecting the molten pool and the molten metal which is flowing from the electrode. In addition to this limestone, there will be additions of deoxidizers as well. Say for example, calcium fluoride can be present in the range of 30%. Other deoxidants like ferromanganese, ferrosilicon or ferrotitanium are also added for removing the oxides from the well pool. In addition to this, alloying elements will also be present in the low hydrogen electrodes. Alloying elements like ferrochromium, ferromolybdenum, ferronickel may also be present in the flushes. The binder most commonly used will be sodium, which in case of sodium, the polarity will most probably be DC positive polarity, whereas for potassium silicate, it can enable both DC negative and positive, and also permits the use of AC current. The penetration cara of basic electrodes are very similar to that of rutile. But rutile will have a better surface finish than the low hydrogen electrode. The slag cover will be heavier than rutile, but can be easily controlled, and it also, the presence of certain elements will also enable it to be used for all position welding. The slag is not as easily removable as with respect to the cellulose electrodes or rutile electrodes, but the low melting point will make the slab entrapment very difficult, and the defects due to slab entrapment will be very minimum in low hydrogen electrodes. The chemical action of the slag that is produced, which is basic in nature, will ensure that the well pool or the molten the well metal produced will be much cleaner, cleaner in the sense will have minimum impurities, will have high quality in the sense will have a better strength, a better mechanical property, and also with respect to the impact toughness or the notch toughness, 7018 or low hydrogen electrodes are are exhibiting much better tensile as well as notch properties, notch toughness properties. And another feature of the electrodes are it is very resistant to solidification cracking, and are tolerant much more than that of rutile and cellulose electrode. Talking about solidification cracking is a very interesting phenomenon in building, where the cracks are formed basically due to various reasons. Like one of the reasons will be the composition of the base metal, the composition of the welt metal formed, then due to excessive residual stresses, then due to the excessive travel speed. The other thing is due to the elliptical or tear-shaped pool of the molten metal formed. The molten metal normally will be having a tear-shaped. Then another reason would be the presence of impurities. I will have a separate presentation of solidification cracking due to its importance. I believe that you people shall be educated more on solidification cracking, as it is one of the most commonly found cracking defect, also rebuild defect, which forms a visible crack longitudinally on the weld formed. The basic electrodes, as I told in the beginning, are also known as low hydrogen electrodes. Unlike the rutile and cellulose electrodes, the low hydrogen electrodes shall not have any moisture content for the stability of the arc. So, uh, if at all any moisture content is present, it shall be removed. The most commonly used method to ensure that moisture content of the electrodes are removed is baking of the electrodes. So the baking of the electrodes, there is no hard and fast rule, or there is no general rule for that. We shall strictly follow the instructions of the manufacturer. In most of the cases, but it's not as I told general, though I have written general here. In most of the cases, the electrode shall be taken to around 400 degrees Celsius to remove all the moisture content present, and then it shall be kept at a temperature of around 120 degrees Celsius during the time of work. The figure shown here to the left is a mother oven. The mother oven is basically the place where the electrodes will be kept until it is taken for work. And the figure which is shown to the right is a portable oven where the electrodes taken from the mother oven are kept at temperature of 120 degrees Celsius and taken to the site where the welding is performed and connected to a power source. And whenever an electrode requirement comes, the lid is open and one electrode is taken, and the lid is kept closed so that the electrodes inside the portable oven is always at 120 degrees Celsius, and thus prevented from direct contact with the atmosphere. However, certain manufacturers provide the electrodes in hermetically sealed containers or vacuum pack containers. One of that is shown here, but it is the picture shown here is an open one. This type of containers will ensure that the hydrogen content will be very less, or the contact with moisture or atmosphere is minimum. Talking about low hydrogen electrodes, um, the the hydrogen content in per 100 gram of weld metal will be only in the range of 5 ml, whereas if you may recollect in our last slides, it was about 20 ml or so. So wherever these low hydrogen electrodes are used, it is certain that unless and until certain contaminants or moistures are introduced, the weld produced will only have a maximum of 5 ml per 100 gram of weld metal will have only around 5 ml hydrogen content in that. The applications due to the high quality of the in the second point I have shown in slide 6, you can see because of the high quality of the well produced and due to the high strength, these are always used for critical applications like um, say for example underwater welding, boiler welding, then offshore structures, wherever there is a chance for solidification cracking, wherever there is a chance to have more dynamic loading, that or a more impact loading, we prefer the use of low hydrogen electrodes. These electrodes, for those electrodes which are taken directly from hermetically sealed packs, it is claimed by the manufacturer that it can be used up to 12 hours without keeping in a baking oven. But normally it is preferred not to take that risk because the whole idea of using a low hydrogen electrode is to ensure the quality of the well produced. But we always prefer to use a portable oven whenever we need a very high quality weld to be produced by 7018 low hydrogen electrodes. This is what I just mentioned before. Wherever high quality or radiographically or ultrasonically clean weld requirements are there, we prefer these basic electrodes or low hydrogen electrodes. These, as I have told before, have a reputation of giving very good choppy V-notch toughness as well as CTOD. CTOD means crack tip open displacement testing. These are basically tested for a very high thickness, and the figure shown to the right is a, CTOD test. And these are basically done for high thickness and not below maybe around 45 mm thick. Low hydrogen capabilities also mean that the basic electrodes would be used for welding very high thick plates and high carbon low alloy steels where cold cracking is a risk. Earlier I was mentioning about solidification cracking. Cold cracking is basically known as hydrogen cracking itself. Hydrogen cracking itself, I think I have told in your previous class about hydrogen cracking. Now, whenever a material is taken to a high temperature, the chemical reactivity of that particular metal increases. When a particular material is taken to high temperature, the solubility of hydrogen for that particular metal will be very high. The thing is that when the welding is over, this particular material is suddenly brought back to a lower temperature. During this time, the hydrogen which is already present inside due to the solubility at high temperature may not escape out due to the sudden change in temperature. So at that particular room temperature or at a reduced temperature, the metal will be at a supersaturated condition of hydrogen. So what is hydrogen will always have an affinity to go out because that is in a supersaturated state. So when this hydrogen will try to get out of the metal, out of the solidified molten metal, it will make a path, it will make a path to escape, and these are known as hydrogen cracking. The path through which the hydrogen tries to escape out will eventually form a crack, and usually it is known as cold cracking because it happens during after solidification. It is also known as delayed cracking because it takes some time for the hydrogen to escape out and then form hydrogen cracking. So this is the main reason why whenever we do a radiographic test or any sort of test after a welding is performed, we do the testing of the weld only after 48 hours or 72 hours preferably, because we give some time for the weld to show the hydrogen cracking phenomenon, because it is a delayed cracking. It takes time for the hydrogen to escape from the the solidified metal. So this is all regarding low hydrogen electrodes. We will discuss about solidification crack, as I have promised, in the next class, where I will explain you what is a solidification cracking, how that can be prevented, what are the basic causes of solidification cracking, etc. Thank you.